In this module, we discuss mainly about the fast convolution techniques, namely overlap add method and overlap save method. Also, we discuss about the fast Fourier transform methods, which involve decimation in the time and decimation in the frequency domain. Fast convolution is essentially the convolution of a long input sequence with the impulse response of a system in order to compute the output. The factor that speeds up the operation of convolution is the usage of DFT and IDFT. DFT and IDFT is involved such that the calculation of the convolution is done faster. Fast Fourier method is a faster, or it's a more efficient method of calculating the DFT compared to the regular expression. Before we begin, let us gather some information on the difference between linear and circular convolutions. Primarily, we know that the equation for linear convolution is something like this. The symbol for convolution is star. To distinguish linear convolution from circular convolution, the symbol used for circular convolution is usually the star enclosed in a circle, or the N which is inside the circle. As we are familiar with the formula, the steps in circular convolution, namely reflection and shifting, is done circularly. In linear convolution, the length of the inputs x of n and h of n need not be the same. But in circular convolution, the lengths of both the inputs must be made the same. If they're not same, we have to append sufficient number of zeros and make it the same length. This step is called as zero padding. Zero padding is not required for linear convolution, whereas it is necessary to make both sequence same length in the case of circular convolution. The output length in the case of linear happens to be length of the first sequence plus length of second sequence minus 1, whereas the output length for circular is capital N, which is greater among the two lengths. There is no aliasing effect in linear convolution, whereas circular convolution exhibits aliasing. Linear convolution is applicable for a periodic sequence, whereas circular convolution is for periodic signals. So these are some differences which will help us understand the topic in a better way. Let us discuss about linear filtering using the DFT method. The problem statement is that we are having an LTI system whose impulse response is h of n. Now to this system, when you feed an input called as x of n, the output of y of n is given via linear convolution between x of n and h of n. The output length for linear convolution is going to be L1 plus L2 minus 1. The same result could be obtained making use of circular convolution, provided we make both the sequence of length L1 plus L2 minus 1. That is, if both are made to be the same size equals to n here, then circular convolution will also give you the same result. Circular convolution can be implemented to generate the answer in a more efficient way if we involve the DFT and IDFT, which we have learned in the previous module as the Stockham's method or the frequency domain method of calculating circular convolution. We are involving the DFT and IDFT in calculation of circular convolution. In turn, it is producing the answer which corresponds to linear convolution. This method is called as fast convolution because it makes use of DFT and IDFT to generate the answer faster. The first method we're going to study under this topic is called as the overlap save method. In overlap save method, the size of the input data block is made to be equal to capital N, where capital N is equal to L plus M minus 1. And DFT and IDFT are of length capital N. Now, out of the total n elements, the first m minus 1 points, they are coming from the previous data block, which is followed by L new data points. Now for these blocks, the endpoint DFT are computed separately. Impulse response of the filter HFN, if it is of length capital M, we increase it to length capital N by appending L minus 1 zeros. And for this, the DFT is calculated. Impulse response of the filter HFN is increased to length N after appending L minus 1 zeros. The DFT of HFN is calculated once and stored. The multiplication of two endpoint DFTs, H of k and Xm of k, from the mth block of the data yields Ym cap of k is equal to the product X of k, H of k into Xm of k, where the k value is between 0 to n minus 1 because each block is of size n. The endpoint IDFT of this yields a result Ym cap of n, where the elements are Ym cap of 0, Ym cap of 1 till the last term Ym cap of n minus 1. It's an endpoint sequence. Now this data record is of length capital N, in which the first m minus 1 points are corrupted due to aliasing. Aliasing happens in the case of circular convolution, and these points must be discarded. Last L minus 1 points of Ym cap of n are same as the result from linear convolution. So hence, in each data block, out of n outputs, the first m minus 1 points need to be discarded. The remaining L minus 1 points are kept, and these are joined together to form the final output. Hence, Ym cap of n is same as Ym of n for n value which lies from m to n minus 1. To avoid loss of data due to aliasing, the last m minus 1 points of each data record are saved, and these points become the first m minus 1 data points of the subsequent record. To start the procedure in the very beginning, we set the first m minus 1 points to 0 in the first record. The formation of the data blocks is shown below. X1 of n is the first block. In the beginning, we place m minus 1 zeros followed by L data points. For the next data block, the last m minus 1 points of the first record is taken and placed at the beginning, and then it is followed by L new data points. Once again, we take the last m minus 1 points from the second block and place it at the beginning of the third block, followed by L new data points. This process continues. Let us consider the problem given here. Find the output y of n of a filter whose impulse response is h of n, which is equal to 1, 2. And the input signal to the filter is x of n equals 1, 2, minus 1, 2, 3, minus 2, minus 3, minus 1, 1, 1, 2, minus 1. Using overlap same method, use n is equal to 4. This problem is to determine the output of a system whose impulse response is provided and input is given. Before you start the problem, we count how many points are there in the input and the impulse response. The input is composed of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points. The impulse response is of length 2. Therefore, since we are calculating the result for linear convolution, the answer is length of first sequence plus length of second sequence minus 1. We are expecting total 13 points as the output. Now let's proceed with the problem. The relation governing the linear convolution here will be n is equal to L plus m minus 1. The blocks are chosen to be n, which is equal to L plus m minus 1. L is the number of data points we take to create each block. M is the length of the impulse response. Impulse response is of length 2 in this particular problem, and L value can be calculated using the value of n. We solve and obtain the value of L to be 3. Hence, from the input block, we will take 3 data points and create the blocks of size 4. We can observe that the blocks are created as first 3 points 1, 2, minus 1, next 3 points 2, 3, minus 2, and so on. We create the blocks in this fashion. Now ideally, you can observe that the final point minus 1, we end the fourth block. Next, we have to create the blocks of size n. To create blocks of size n, the initial block, we are placing m minus 1 zeros at the start. M minus 1 is equal to 1 because m value is equal to 2. Therefore, we are placing 1 0 at the start. So this is the 0 that has been inserted. To create the next block, we take m minus 1 points from the end of the first block and place it at the start. This is followed by the 3 data points 2, 3, minus 2. Next, for the next block, the last point minus 2 is taken, placed at the start, followed by 3 data points. Next, the last point 1 is taken, placed at the beginning, followed by 3 data points. Here we are going for the fifth block, primarily because if we create 4 blocks, we will get 4 outputs, and each output is going to be length 4. And in each block, we will discard the beginning m minus 1 points, or the first point will be discarded due to aliasing effect. So we are left with 4 into 3, 12 points, whereas the calculation has clearly said that I require 13 points in the result. Therefore, we introduce the fifth block, which is created by taking the last point minus 1 followed by 3 zeros because we do not have any data. In the next step, we perform the 4-point circular convolution. While solving problems, convolution is preferred over DFT because we can do convolution in a faster way, whereas a system would perform the same DFT and IDFT in shorter amount of time. To prepare the data for convolution, we have to make h of n to be equal to length n. So we pad two zeros so that it is also of length n. Now we can proceed for circular convolution. To find the output of each block, we have to perform convolution of the block with the impulse response. So here we are expected to do 5 convolutions. Let us do the calculation now. Since convolution satisfies commutative property, we can take any block first. Here we choose to take h of n first because h of n is a same repeating sequence. So for each block we can place the same h of n at the start without thinking too much. So first we arrange h of n in the form of an n cross n matrix, and then we multiply it by the inputs sequence, which is x of n. This results in the outputs that we have shown here, and we get outputs for the 5 different blocks. Once the final output is obtained, now we have to combine the results. In order to combine the answer, we can align the data in the fashion as shown. So we are writing out the outputs of y1 of n, y2 of n, y3 of n, and so on till the very last block. We have seen that the last m minus points are shown as overlapping. Now in each block, we discard the first m minus 1 point. Here m being 2, m minus 1 is equal to 1. So first point is discarded in each block. The remaining points are written in sequence. So this forms the output. The output can be easily checked by computing the linear convolution between x of n and h of n by using a tabular method as shown here. The verification shows that the answer is right. Whatever you calculated, the answer is matching. The last 2 points here are 0. It is not going to affect the answer, but the rest of the points answers are exactly the same. Thank you all.